onboard computers, flight software, command and data handling. There's a lot of different words for sort of what I'm trying to cover today, but basically, when you send a little box to space, there's a bunch of things that you can do with that. There's these educational missions, all these science missions, right? Like taking pictures of the Earth, astrophotography, all sorts of different possibilities. But one of the things that's really unifying them is that they all have data that we want to get down to the ground. So if you can't get the data down, it's sort of not really worth sending up the satellite in the first place. So sort of the first and biggest goal of this, onboard computers, flight software, command and data handling, whatever you want to call it, is getting that data down, getting that mission data down. And to boot, there's a bunch of operational requirements that we have that sort of keep our satellite alive so that it can get these like little pieces of data and send them down. But the most important is just completing the mission, and often that's just getting the data down. So one of the big requirements is communications. There'll be a communications workshop tomorrow, but pretty much what this entails is like you have radios that you need to drive. You need to prepare your packets with telemetry. You need to get everything ready so that you can like send it down to the ground and sort of have a window into your satellite to see like, what's happening up there, 400 miles away, potentially like thousands of miles away if it's on the other side of the Earth. The next big thing is solar panels. This is the most common way of generating power in a CubeSat. People have proposed like nuclear power. I think that's highly unlikely to ever happen, but pretty much when you have a computer, you need some power source and you need to generate that power. And so we use solar panels. And typically like these solar panels would be like, space grade or whatever and like fancy. Sometimes they have like integrated electronics on them for like moderating the power flow. Typically that though would be handled in like the power subsystem of the satellite.
Flynn, if I can just jump in, do you happen to still have those Azure space cells sitting on your desk, or?
I do. They're not out. I can grab one if you want.
I think it'd be good to get a sense of scale for people.
Okay, well, I mean, this is a big box, and this has like 3 solar panels in it. They're probably about like, I don't know, like 8 centimeters aside. They're pretty small. They're very, very easy to break. If you've ever soldered solar cells for like, little IC projects or whatever, they're really fun to break.
Yeah. And since we don't have like a dedicated EPS workshop this year, I'll just take a quick moment to comment on this. Usually here on Earth, like the solar panels you're probably used to are silicon based, which are actually relatively cheap these days, but they're only about 15% efficient. Since CubeSats are at a real space premium, there's not a lot of surface area to go around. Usually they use these fancy pants gallium arsenide triple junction solar cells that not only convert the visible light, but also the IR and UV into electricity too. And they're about 30% efficient, but probably about 10 to 100 times the cost. So there's a whole lot of like engineering that goes into that too, but we're not going to spend too much time dwelling on it.
Yeah, don't worry. Gallium arsenide is just like another semiconductor like silicon, just pretty like replaceable for silicon in terms of like a circuit. So then once you've generated your power, you need to put it somewhere, and typically this will be batteries. And again, because we don't have the dedicated EPS workshop, we're not going to like dive too deeply into this, but basically like you need to have batteries that aren't going to like explode. You need to make sure that you don't explode them by like overcharging them. And oftentimes this will be handled by like separate circuitry that's like either integrated into the battery or as like part of a dedicated like battery subsystem or power subsystem that has like the circuits just to make sure that you're not like overdriving them or whatever. But yeah, basically the command and data handling system needs to be able to draw power from the system and direct the power system. And then the next sort of big thing is the attitude determination and control system. And this is often a subsystem in its own right because it's so big. And sometimes it'll have like a dedicated computer that's, solely for the attitude determination, for figuring out, how the CubeSat's oriented or how the satellite's oriented, and then controlling it to be reoriented. But it has to be very integrated with flight software because you kind of need to know where you are in relation to the ground station. There's also a lot of sensors that are, you need to see okay, what is this sensor telling me? What is my rotation? What is the gyroscope saying, et cetera. And then also it's software. So it has to be running on some sort of computer somewhere.
Yeah.
So
Flynn, yeah. Oh, Flynn, sorry, if I can just real quick.
Sure.
Yeah. I do want to take a second to plug my own workshop on Thursday just to dive into attitude determination control systems. Oftentimes you hear us abbreviated to ADACs. And I do want to just take a second just to kind of clear it up. I know for people who are not aerospace, it can be confusing sometimes when we refer to a control system. We're not talking about commanding the satellite. We are talking about commanding a satellite, but not to do things like compute or take pictures or things like that. Control systems usually refer to the actual orientation of the satellite. What is it pointing at? Generally, CubeSats don't have propulsion on them, although more and more are having propulsion. So the attitude part is where is it pointing? And then the control system is how do you move it around?
Exactly. So there's sort of two ways you can do that. You can do that with these magnetorquers that are just a big spool of wire that interacts with the Earth's magnetic field, or you can do that with these reaction wheels, which basically are wheels that spin sort of like a bicycle wheel and then reorient you. And as we said, oftentimes this is a separate system, a separate computer that's dedicated to this task of orienting the satellite. And it does have to interact pretty heavily with the other subsystems. And so oftentimes that interaction is handled at the level of the flight software because you need to know where you are so that you can figure out how to point your antenna so that you're pointing at the ground station when you want to turn on your radio and send the packets down that have that juicy data. So then sort of one more big thing that's pretty important is having some sort of storage mechanism for storing data on your satellite, because oftentimes these sort of data collection and data downlink regimes are separate on a temporal scale. So you need to make sure that the data that you've generated is stored safely so that you can downlink it when you're in range of your ground station. You can also keep logs of sort of the operational status of your different other subsystems so that when you want to downlink them, I see somebody put something in the chat.
Oh yeah, they were just asking about the pros and cons of torquers versus wheels.
Oh yeah, that'll be, if you're interested in that, you should definitely go to Michael's attitude determination and controls workshop tomorrow, or sorry, Thursday. So yeah, you need to have storage so that you can keep your payload data. This is the important stuff that you're generating, maybe you're taking pictures of the Earth, and then also logs of how the subsystems are faring. Are they doing their jobs correctly? Have they errored out? What is the temperature? How much solar power are we getting? That sort of thing. So you can send that all down and then have sort of this package that you can look through to ascertain how well your satellite is performing. Okay, so we talked a lot about sort of the task at hand. So now we're going to jump back a little bit and talk about what we're going to use. What are we going to spec out, the hardware? So you need some sort of computer. You need a thing that can do smart stuff to do all these tasks. So there are a bunch of options. Here are a couple of Raspberry Pis on the left and then BeagleBone Black on the right. These are just cheap commercial off-the-shelf electronics that people have been using for actually some years now, just inside of their satellite. And the reason this is sort of one of the things, or the reason that people use these is because they're cheap and they have pretty high like compute capabilities. Whereas if you're buying something that's like dedicated to space, it's sort of a little bit less like, how do I say this? Like less, it's slower because it's like old. So there are a couple of considerations you have to make when choosing your compute platform. First is sort of like the architecture. And oftentimes they will be more on like the ARM side. x86 is like what a lot of people have in their laptops. This would be like a Intel compute platform. But the reason that ARM is so popular is because it has, it's open source. So a lot of like the small like chips that I was showing earlier, like the Raspberry Pis use ARM like to make the chips. And this isn't really important as far as like what you'll actually be doing when you're like picking the chip. But basically like ARM uses like a simpler instruction set, which is more commonly used when we have like radiation hardened chips. So we're going to get into that a little bit later in the presentation, but pretty much what you need to remember is that like ARM is pretty popular and x86 and other architectures are less popular in space. Another thing that people use is these field programmable gate arrays or FPGAs. You probably also don't need to really remember this too much because these are like expensive and used by fancy people. And they're pretty good for like radiation tolerance. They're also pretty good when you have something that needs to be done like really fast. So they're used a lot in like cameras. You'll have to like pre-process an image. But for the most part, you're probably not going to be like putting one of these in your CubeSat unless it's a specific part of your mission, or if you have a lot of money, or potentially like 10 years down the line, they could become cheap enough. Okay. Do you have any questions to this point? Awesome. So moving on, mechanical considerations. Pretty much like you need to have your computer and you need to like connect your computer to other computers and other components of the satellite. And, originally like people probably just made these computers and like then figured out the wiring. Then someone came up with the idea of having like a bus, which is pretty much like a standardized way of interfacing these computers. And the reason that is so useful is because then you can just stack them up like this. And then you'll have a bunch of like, computers. So you see on the right, there's like some different like names. What everyone thinks they're using is PC-104, but I'm actually forgetting now, it's just slipped my mind, but there's actually like, the most common one is not PC-104, but everyone just calls it PC-104 because that's like, I guess, easier to remember. So then finally, we have like, I guess this is, oops, okay, my slides are a little bit out of order. So yeah, one of the other like important tasks that we have is managing our thermal system. So this is pretty much making sure that we don't get too hot or too cold, because it would be really bad if like, say, our batteries exploded or if we weren't able to discharge them because they were too cold. So yeah, again, this is out of order. This is not part of like the mechanical consideration. Well, it is, but yeah. Okay, so yeah, basically, one of the other like considerations here is that like you want to use a little, like as little space as possible, right? So you want to combine things where possible. And this here is just an example, Pi cubed, similar to what Cal Poly is using, Polycubed. It is a computer that has unified a bunch of these different tasks into sort of one board that like, functionally has the like battery charging, the radio, GPS, other stuff for like attitude control stuff, all integrated into one board. So instead of having this like big stack, you can have just like one board that's doing a lot of things. So, you know, that sounds really nice. And a lot of people have like looked at this Pi-cubed board and said, okay, well, if I can buy one of those, you know, why wouldn't I do that? What's the downside? So Pi-cubed is meant to run this CircuitPython, which basically is a like distribution of MicroPython. It's like Python that like does stuff. And pretty much it has like three components. It has, as described as the makers, by the like makers, Adafruit, it has a virtual machine that's fast so that it can be run on multiple architectures. So think back to like the ARM versus x86. It can sort of run on different architectures, or sorry, different like chips. Typically it would be like smaller variations. So like 2 different ARM chips it could run on. That doesn't require a lot of modifications. The second component is sort of like this supervisor software that like connects that VM to the hardware and like, you know, interfaces that. And that's something that you would have to change for every chip. And then there's also APIs for hardware access. So it's pretty simple. Like you can just, once you have like the bootloader, which is like the thing that loads the operating system onto the computer at like a super low level, once you put CircuitPython on, like you can just plug it into your computer and get to like writing Python. Like there's no compilation step. It's packaged with an interpreter. So it's pretty easy to get started. But as I'm sure some of the people in this meeting have, or have a bunch of stories about like, you know, why CircuitPython isn't too good. So, you know, one of the things that you might think like, oh, well, we should use Python because like, you know, there's a bunch of libraries for Python that like maybe you're familiar with from some of your data science classes, or I don't know, just like random projects. But unfortunately, you don't actually get a lot of these libraries in CircuitPython because, you know, they're written in like other languages, or like they use tools that aren't available, or they require larger amounts of memory. So why would you actually want to use CircuitPython? Well, pretty much what you get with Python is memory safety, or CircuitPython is what you get is memory safety. There's, you know, less of a chance of accidentally like allocating memory that's been already allocated, or, you know, reaching a null pointer exception. And you also get the syntax of Python, which is super simple. And, you know, particularly like desirable when we're, you know, all students and want our projects to be as accessible as possible. You can also write C code if you want something to be like really fast, because Python is pretty slow. I don't know if like anyone's like heard like these people like debating like, oh, Python like is too slow for space. But, you know, one of the arguments in favor of CircuitPython is that it doesn't necessarily matter how fast it is, because oftentimes you're only running the CircuitPython code for a very small portion of time. So another popular option is C++. And this, you know, language has been around for a super long time. And some of the advantages are that like it's more low level, so it's easier to like interface directly with components, and also like implement directly functionality that might be lacking in CircuitPython. Other options are going with sort of the Arduino framework that like helps pretty much write C++ or MicroPython. So MicroPython is pretty much like a different distribution. It's like very similar to CircuitPython, except it has actually has more libraries. So it would be more analogous to that like picture that I showed that had all the Python libraries. More of those are present in the MicroPython distribution. And then also the robot operating system is sort of like, I mean, it's sort of like half and half, like a framework for writing software and a language. But there are some features of the robot operating system that like, such as like message queues and that sort of stuff that like make it, you know, an advantageous or like some sort of choice that you could make for Python. Can you do true RTOS commands in Python? Awesome. You cannot. So I was just about to get onto that. So, you know, once you've like picked a language, or I mean, it's not necessarily like something that you're picking like in order. But you know, another important thing is like, what sort of operating system do you have running on your computer? So if you're using CircuitPython, that doesn't have an operating system per se. It has this CircuitPython VM. And other options are like, you know, real-time operating system, which allows you to do things like in real time. So if you have like some sort of requirement for like maybe you're doing like some laser communications or something, and you need to like, as soon as you get like the first pulse, you need to like send a pulse back or something. Then you would want to use a real-time operating system because it's enables you to like interrupt and go directly to that other task because it has like a super high priority to come in. So there's sort of the two like real-time operating systems options that people use are like FreeRTOS and VxWorks. VxWorks is like Wind River is the manufacturer or something, but it's closed source, so it's not as good. And then also Linux. Linux is super popular for space because it's like open source, easy to work with, and you know, like that it makes it easier to get your stuff done. Notably, like Windows is not here, and obviously macOS is not here because those are like giant operating systems that are heavily focused on like the visual component, which doesn't really matter so much in space because we don't have like a screen to like type on our computer. And then finally, another option is just to write code directly for the computer, as we say, like bare metal. But I don't really see why you'd want to do that. I guess the main argument is that like you get to do everything yourself, and it gets to be like, you know, super fast as, you know, performance requirements exactly as you need them. But in my opinion, there's no real need to do that because like these frameworks and these operating systems exist for a reason. And it's that like we want to spend our time building fun satellites. So pretty much the four major trade-offs when picking like a hardware and software stack are power requirements, like how much power does it take, how easy is it to use, how fast is it, and how reliable is it? Like, you know, has it been flown in space before? And, you know, will it like crap out on us, or will it just like keep working forever? Awesome. So when it comes to actually like getting in and writing your flight software, there's a couple of different like frameworks for writing the flight software. And going back to what I was saying earlier about like this argument against writing code for bare metal versus writing it for like an operating system, if you use a framework, you have the advantage of like the basic things that you need to write flight software, like, you know, scheduling, sending messages, are already implemented for you, and you don't have to worry about re-implementing them. And that's just saved time for you because you get to spend more time working on your satellite instead of writing more boilerplate code. So the analogy I'd give is like sort of like pancake mix. Like, sure, you can make your own with like your favorite brand of almond milk and, you know, pink sea salt, but there's not really any need when you can go to the store and buy pancake mix that, you know, will allow you to spend your time making the actual pancakes and eating them. So yeah, the core flight software in particular, core flight system, this is NASA's like open source offering for flight software, was influenced by all of these missions you see here. And pretty much like the paradigm before that they had was they would like build the flight software for a mission. Has anyone here written in Rust? Rust is another super good option. We can definitely like chat about that after if you're interested. But yeah, pretty much like people would like write all the flight software for their like satellite, and then they would like, you know, just like store it on some server somewhere. And then like when the time came to do another mission, they would just like dig it up and like copy it over and start like rewriting it, which pretty much like it kind of works, but like it's sort of like, you know, this is why like libraries exist. Like you want to be able to like use the stuff that is like, you know, very commonly used, like pancake mix and like, I don't know, like cake mix or brownie mix or whatever. So while we're on like programming paradigms, there's a bunch of different like ways of like writing your code. You can write it like object oriented. You can write it sort of event based, like, you know, when something happens, do something else. Like when we're over the ground station, downlink the data. But object oriented is by far the most common. It's definitely okay if like you don't know what that means, but basically, the idea behind this is that you want to encapsulate your data as well as possible. And so going back to like the overarching goal that we have of like getting our data down, this is sort of like, you can kind of see clearly why you would want to use this object-oriented programming method, is because like you want to like keep all your data like as pure as possible and make sure you're not like mutating it or like doing things to it that you shouldn't be doing. So what does the flight software actually look like? We've talked a lot. I've talked for like a really long time about like, you know, picking different things and like different options for like, you know, different things that you can use, ways you can like, you know, languages you can pick, etc. What does it actually look like? So most CubeSat missions use what's called a state machine. And I mean, there's a couple names for it, but basically what it is like, you have like different states that your satellite can be in. And there's a finite number of these states, right? Like maybe you're doing nothing, like you're just sitting there, or maybe you're like actively recharging, like you're pointing your solar panels at the sun, or maybe you're like in a mode that, you know, points you directly down to like take pictures of the Earth or something. And the reason that we break it up into these, you know, finite number of modes is so that it's easier to test. And it's also easier to debug because there's only like a certain number of states it can be in, right? Like it would be a lot more complicated if we had like the status of the attitude, determination, and control system sort of separated from like the communication system, because like then you'd have 2 times as many combinations, right? Like, or 2 squared, because you'd have like, you know, it could be on and this could be on, or this could be off and this could be off. Whereas if they're like tied together, then it's a lot easier to debug. So these state machines actually occur like at a couple of different levels. So you have like sort of the overall state machine, which is like the mission states. I ripped this left one from Cal Poly BroncoSat. I don't know how old this is, but pretty much you have like this overall like mission states, like, you know, you deploy, commission, and then you start executing operations, and then eventually you'll have an end of life phase. You also have like individual state machines for like your power system, for example, like, you know, based on the power system, like, are we charging, are we discharging, and that sort of thing. And they're all sort of like different lenses of like looking at like what's actually happening in your satellite. So one of the big takeaways here is that like diagrams are very important for developing software, because they allow you to clearly communicate, or developing good flight software, they allow you to clearly communicate what's going on before you've actually written the software, so that like you can have a pretty big discussion about this and talk about stuff at a pretty high level before you actually go and like implement the flight software. Okay, another one of my things got like, okay, this is another slide that's out of order, so I'll just skip it, I'm sorry. But okay, testing. So once you've written your flight software, you kind of have to make sure that like it's going to work, because we like satellites that work, and we want to make sure that your little CubeSat is going to do what you're expecting it to do. So testing is very important. You 100% have to test. You have to test a lot, because this is how you're going to find the errors in your code, right? Like you need to make sure that like when you're in the like, attitude pointing down and like radio on state, like you haven't accidentally over constrained your resources or something. And this is another reason why a finite state machine is a good choice for CubeSat. It's because it makes testing a lot easier, because there's sort of less different like branches through your code and less possibilities of like, ways that you can get from A to B. Luckily, there's a lot of different frameworks you can use, as well as like dynamics modules, all sorts of things for full, everywhere from like a simple like orbital simulation to see like if we're on this side of the Earth, or like, after this many minutes after we've like deployed from the CubeSat deployer, all the way up to like a full operational simulator that NASA uses. This NOS3 in the upper left is used by the like independent verification and validation facility to like completely test some of the CubeSats that they build. It's pretty cool. It's on GitHub. You should take a look. There's also a couple of like frameworks you can use. I'm sure people have seen this on like GitHub, Jenkins and Travis, for like automating your testing so that you can like make sure that as you're writing code like into the future, you're not like introducing new bugs that are going to completely break your satellite. So it is pretty important that you like set this up in your GitHub repo just to make sure that like your code's doing what you're expecting it to do. And there's a lot, like I could say a lot of stuff on testing I could do. Like I could talk for like a couple hours just about testing. But pretty much the gist of it is that like you have to start testing at the lowest possible level and test like the individual functions first, and then from there like build up in sort of a tree structure. So something that I've seen in my time at NASA is that like definitely more than half the team is focused on testing. You think like, it's a software team, flight software team, like probably like everyone's going to be writing flight software, right? Not true. Testing is very, very, very important. There's no way that I could emphasize enough how important it is that you test, because we really want our CubeSats to work. And the only reason that you would potentially not want to test is if like you were like going really fast and like you needed to get it up there, and like that's sort of the battle that you're facing with a CubeSat. Pretty much like the reason CubeSats were invented is because people wanted to like lower the development time, and testing sort of like increases your development time, because like the more you test, like the more time you're losing that you could have like your CubeSat be in orbit. So all the more important that you're organized in your testing so that it doesn't like take up too much time, which is why it's important that you set up these and use these tools, because they make your lives a lot easier and they make it easier to test, which increases the overall probability of mission success. So what if we fail in orbit? Say, the testing didn't work. There's like some sort of error. On large, there's sort of like two different classes of error that I will generalize to. There's like algorithmic errors, which are like a programmer made some sort of error. Like, I don't know, could be a million things. Not necessarily you, it could be in like some sort of library that you used. We'll just lump those all together. And then there's like physical errors, like your computer gets zapped by like, a stray proton or something, or it gets fried, it gets too hot, something like that. There's sort of these two different ways of like classifying the errors. So how do we deal with those? One of the most popular ways is having like a voting system. So you have like 2, 3, 4 computers that are running the same code with either the same sensors or a different like matrix of sensors. So maybe it has like a different, magnetic field sensor, or like a different accelerometer. And they're still making the same decisions. And then they would say like vote or something like, oh, like I think that we should do this. Well, if there's, one odd one that's out, it's more probable that one is like the broken one. So then that output would be ignored and the satellite would not do that decision. This isn't particularly common on CubeSats because they're so small. Because, like you don't want to like use your valuable space, like, you know, with like an extra computer. So what can you do instead? Well, PyCubed, which is the computer that I showed earlier, has a watchdog timer. And this is something that like hasn't become super popular. Well, I mean, it's becoming very popular now in CubeSats. And basically what it does is it's a little like chip that if you don't talk to it every second, it'll reboot your computer. And the reason that's advantageous is because if it can catch like some of the algorithmic errors and also some of the environmental errors, right? Like if you like have some sort of null pointer exception or something like that, or like, you know, you have like a cosmic ray hit it or something, this watchdog timer can catch you and can sort of get you out of a bind. And that is one of the advantages of using CircuitPython. You can also go for like full up radiation hardening. That's a good question. So Victor asks, how do you maintain your state when you reboot? So the best way to do that is either to like have persistent data storage somewhere. So you could use an SD card. That's not something that I was able to work into the presentation. Sort of SD cards have, you know, advantage that they're like small and easy to work with. But one disadvantage is that they're like more prone to radiation effects on the long term. But yes, you could store it in an SD card. You could have like persistent storage somewhere. There's also memory that's like sort of like more integrated into your computer that you could use potentially for persistent storage. Yeah, exactly. You could use like EEPROM. That's pretty popular. Usually more in like bigger satellites when there's more space, so you can like fit more of it. And then the other thing you can do is like just write your code in such a way that like you'll still fall back to your same state, like when you get rebooted, because like, you know, it's like, you know, if you're on this side of the Earth, you're doing this. So if it initializes, it would figure that out. Like also feel free to unmute if you have like other questions. So yeah, you can also go for like radiation hardening. So this is a process that takes place at like the like little chip, like manufacturing scale. And as far as I know, it's not particularly common on like university CubeSats just because it's so expensive. But if you were able to get your hands on like a radiation hardened chip, I'd say like go for it. Like that's a super good option. So yeah, the sort of another way of defending against like these physical radiation effects is with shielding. You can use shielding for things other than radiation, like you could have like sun shielding to make sure that your satellite stays the same temperature. But pretty much like the most important, or the reason that shielding exists is to protect against radiation effects. And these are both like single event upsets in the short term, like, you know, having a bit like flipped might cause your entire like program to crash. And then also effects in the long term, just like killing transistors over time. So next thing I want to mention is like software updates. It's highly conceivable that you'd want to update your software on orbit because like maybe you didn't have a chance to finish testing, or like maybe you just want to add a cool new feature, or like maybe you didn't even finish it because like you were busy like finishing your satellite. So like depending on like what you're using, this can be like easier or harder. Like with Linux, it would be like pretty easy. With CircuitPython or like PyCubed, it's not like it's not supported to this point. It definitely will be. That's something that like they're working on. But yeah, like pretty much you want to be able to update your software if you can. And like there are some dangers, like you could screw up your entire like thing, like you could like break it. If you uploaded new software that like doesn't work, like it doesn't be able to like phone home, then you're kind of like screwed. So the takeaway there is just like keep a copy of the old version. and have a way to get back to the old version of the software. Because especially when we're using like satellites that are like, really far away, you can't just go up there and like reboot it. Like you're kind of just like screwed. Okay, and so then the last thing I wanted to mention is like how you organize your code. Definitely should use like revision and source code management tools. Probably not Subversion, but any of the other options are fine. Make sure you're using that. There's a lot of like good resources online. This will keep you organized, will keep your code organized. It'll like help you make fewer mistakes, and it'll help you like figure out when you made those mistakes. And lastly, a couple of resources. As you're like looking and getting started, sort of the best places to start for software in particular are like the frameworks, like Core Flight System. CubeOS is an open source operating system that's like based on Linux. Fprime is JPL's like CubeSat flight software, and then PyCubed. Previous missions, these like 3 missions that I mentioned, along with a bunch of others, have pretty extensive like repositories of information online that you can go and just like look at their code and like see what they wrote. You can also look at the Virtual Apollo guidance computer. This won't be particularly helpful for your CubeSat, but I thought it was pretty cool. There is code that you can compile and run yourself that is like was running in Fortran on the like actual like Apollo lander and the Apollo lunar module. It also, there's like some code, schematics. It's super cool. You can use Sat Search to find components. Also, Google is pretty good for helping find like things that have been flown before. And the last thing that I wanted to really mention is that like flight heritage is pretty important. Basically, what this means is like you have a component and you've flown it before and it worked, so therefore you should consider using it again because it was good. So questions?
Flynn?
Yeah, what's up?
Hey, Zed. I was wanting to ask about Rust earlier. So we're
yeah.
looking at using Kubos. In
Yep.
fact, we got a meeting with one of their reps tomorrow,
Nice.
and one of the options, the 2 big options that they kind of have that is that, excuse me, you can do a RTOS system or Linux, and they give you 3 languages that you can choose, that you can write things in: C, Python, or Rust. And
Okay.
I've heard people really like Rust for like multi-threaded applications. And the way Kubos is kind of designed, it's like a microservice architecture where like each of your subsystems is basically a service, and it runs its own thread, or at least it shares thread processor, and then spits back information. So you got a lot of things running asynchronously. So I think Rust, I know C and Python, but I don't know Rust that well. So it's looking like it's worth the effort to learn. Anyway, I just wanted to ask you a little bit if you have any experience with that.
Yes, you should pick Rust. Rust is a really fun language to write in. I particularly enjoy it. We're like in SSI at Stanford, we're not using Rust. We strongly considered it, but like we ultimately decided to use CircuitPython, much to my own chagrin. I voted for CircuitPython because like I thought it would just be the better choice for our current mission. But if you have people who want to learn Rust and like you're considering it, like you should absolutely do it because it is the future. Like in 20 years, 30 years, NASA will be using Rust, hopefully.
Thank you.
Why would people be using Rust instead of like C and Python?
The reason Rust is really nice is because it's memory safe. And then also, as Ed mentioned, people like using it for like multi-threaded applications. It's also just like fun to write in. Like the infrastructure is there. Like it is clearly like designed to be fun for the programmer. Like the package manager is really cool and intuitive. It's not like I don't even know what like the C package manager is. Like, is there one?
Flynn, so MJ's asking if there's any sort of like flight testing shielding for things other than radiation.
Oh,
yeah.
So depending like at what scale we're talking, like the ISS has Whipple shielding, for example, which has like pretty much like these 3 or like 4 layers of like I think it's Mylar sheeting that like basically when like a micrometeorite crashes into it, it'll get like broken up, it'll sort of like burst. There's also sun shielding. For example, the James Webb Space Telescope has, again, like 4 layers of Mylar for a different reason. This is to protect the sensitive electronics and keep them really cold. You might need some sort of shielding like that, temperature shielding, in case you have like a camera that you want to like use to take pictures of the stars or something. You have to be sure to keep those really cold because one of the things like the dark current is basically like when it gets hot, it like starts getting like there's like pieces of like little like dots.
It gets noisy. Yeah.
Exactly, noisy.
Yeah. So, the way that like digital cameras work, right? It's just turning usually photons into electrical currents, but for most, I mean, just due to physics, like heat can also be turned into electrons. So when sensors are hot, they have like a noise floor, right? And that can pollute your data, right? If you need really accurate scientific data, or like say you're like taking pictures of the stars for a star tracker, the star might only be like, 3 pixels wide. And if you have like 4 pixels of noise right there, then, oh, well, I guess that data point's totally out the window. Yeah. I would say that generally though, like for most CubeSats you would do at a student level, shielding is not really that necessary. Yeah.
Specifically, we are actually looking for shielding for while our CubeSat is sitting in the clean room to protect it against oxygen and moisture. So that was more, I guess, what I was asking about. Sorry, I should have been more specific. But yeah, have you guys heard of anything like that or?
I mean, nothing in particular. Like, I would say that's like probably something you could work out with the lab. Like, that seems to be something you probably want to handle at like maybe the lab level. Like, make sure that the clean room's like appropriate for construction of the satellite. What in particular is like the worries? Or like some number that you have, or like some sensor that like can't withstand some amount of oxygen?
So our payload is comparing perovskite solar cells to silicon solar cells, and perovskites are really sensitive to oxygen and moisture. And in the clean room, we can't really set the conditions. And so it's going to sit for a minimum of 90 days in this clean room where it's going to be exposed to those things and the atomic oxygen in low Earth orbit. So we're looking for a way to protect the solar cells without basically reducing the amount of sunlight that they get.
I don't know of anything like that you could just buy off the shelf. You could probably make something that's like a big box that like maybe you fill it with like nitrogen or something. And you have like the gloves or whatever. I don't know, Michael. Have you heard anything that would be like helpful?
Yeah. It's an unusual set of requirements for a space mission. I would say like if it just needed to be stored, something like Flynn's suggesting, where you just like purge a box with like nitrogen or something, that's probably like the easiest and cheapest way to handle it. The alternative could also be to put some kind of like some kind of cover over your sensitive like solar panels. The issue with that, of course, would be you would need to remove that cover once you get to space. So the simplest way I could think of is just have like a little door and a spring hinge. The door like sits totally flush with the solar panel, which could have some issues in and of itself, but the door sits totally flush. And when it gets to space, the door pops open. So theoretically, right, you're not exposing it to like just atmospheric oxygen. Because one of the tricky things is that you can't control the satellite at all once it's in the deployer, right? If it goes into the deployer and then the rocket just sits there for like 4 months because it's a Delta IV Heavy and it has like hydrogen leaks everywhere, sorry, but you're just totally screwed, right? So yeah.
Yeah, it's a weird thing to consider. Like you think space, right? Like no moisture, no oxygen, but it's actually Earth. That's the problem. But yeah, thank you.
Assemble it in a vacuum chamber.
Pretty nuts. If you had, well, you see, someone's got to call Harvard, right, and ask for their like robotic arm, or Brown. I think Brown's trying to do the robotic arm on a satellite. I wonder if they're going to call it the Brown arm. They better call it the Brown arm. Yeah. Any other questions about like flight computers or flight software, guys?
I had one more if nobody else is going, if nobody else has something. I
Go
was
for it.
curious about, you were talking earlier about the BeagleBone, and we were looking at ISIS has their own like kind of like their own onboard computer package, but it's much more expensive. And we went back and we called the guy, and obviously he was really big on, well, we did durability testing and flight hard and stuff. But I couldn't help but wonder, is it really worth because it was like $8,000 versus a BeagleBone Black, and I'm like, is it really worth all that extra money?
It's not worth it.
Not.
It's not worth it. You're right. It's just a BeagleBone Black that they've like added some other like stuff to.
So if we get one with the right profile and the right bus to attach to the other cards in our satellite, we're just as good with a BeagleBone Black. I mean,
That would be my take. I don't know if anyone else has like a.
Well, I for sometime last week, I was actually looking into that specific ISIS onboard computer. It's an Atmel part. It's basically a Linux computer. I'd say it's pretty comparable to the BeagleBone processor. So it runs Linux. It can also run CubeOS as well. I don't think there's like too big trade-offs between using either.
yeah, I looked at the specs and I just couldn't see that big a difference. And I was like, is it worth, because it's $8,000 or something for that. And it's just like an ARM 32-bit processor with two 2 gig SD cards that you can plug in. You know, it's just, yeah, I was suspicious about it, but I just, it was hard to get people to say one way or the other whether they thought it was really worth it.
Yeah. Ed, if I can sort of come at it from like a program manager's take,
Sure.
like the $8,000, you're not paying for the electronics. The electronics probably costs like 10% of that. You're paying for the engineers, right?
Yeah.
That designed and then built that, because there's such low volume components. They sell maybe like 10 of them a year. And if it takes one engineer like the entire year to develop it, then well, you're paying his salary.
Yeah.
And so like the value proposition of commercial parts, I think is only really true if you're buying like an entire system from one manufacturer, right? Like if you buy your computer, your batteries, your solar panel, basically everything from ISIS,
Right.
then their value in paying like $100,000 for that is probably there, because
Right.
they've
Which we're not
designed
doing.
it.
Which we're
Yeah.
definitely not doing.
Well, yeah, like you probably can't afford it. But if you could afford it, the value is that it was all designed together. So it's all probably going to work together. And then you won't have to spend your own time to figure out like, oh, dang, right? Like, how am I going to get my radio to talk to my batteries?
And we're integrating we were looking at doing from them, we were looking at the onboard computer, the transceiver board, and the antenna. So they had those 3 parts and a magnetorquer board. So we were looking at maybe buying all those 4 points. So there is some of that. We are kind of buying a fair amount from the same sandbox. But and the magnetorquer looks really good. Like the magnetorquer and transceiver board will look like good options on their own, just in terms of what they provided and their form factor and power. It was the computer where I was just kind of like, is this really worth the money? And like you said, the integration factor, the fact that it's the same company that built the other things. I mean, would you guys think that sways it? Would that swing it for you?
I think it's almost like buying Apple, right? Like if you can afford the entire ecosystem, then it's amazing. Like it'll probably all work together really well. But if you were only going to buy the AirPods Max, I unfortunately cannot recommend you only buy that, right? Like
yeah,
that's
great chip, that awesome chip. Yeah. Okay. Thanks. Yeah, That's kind of where I was thinking, but yeah, it's just the fact that it works well with it, and the company's been good about support. That's the other thing. That's one of, like, for the operating system, we're looking at Kubos, and Kubos is really well tested with the ISIS boards, and I really like their Slack channel because people respond really quickly when you ask questions on Kubos.
Yeah.
Which I mean, CFS and F Prime look good, but it's been really hard to find anybody who's actually willing to answer questions about them.
Yeah. Like I would definitely say, like, when you're doing a cost benefit analysis, really I think the biggest thing to consider that is usually not considered is just like, when like the money that you're saving by not buying a commercial part, you're going to spend an equivalent in not money, but like your own personal time as like student engineers in order to make a comparable solution, right? And so if you as a team are willing to make that sort of sacrifice, like spend a lot of time just engineering, then you can probably, justify the cost savings. But like everything has a cost, right? It's either going to be like a labor cost, right? If it's not like a financial cost, it's a labor cost.
Thanks.
Yeah, good question though.
Question for BroncoSat specifically. The diagram behind you has like a label that says Jetson Nano on it. Can you talk about that?
Yeah. I'm glad you're actually able to read this. Yeah, BroncoSat is the mission for BroncoSat is actually to validate that you can run an AI machine learning algorithms in space. When we first pitched the mission, we were joking that we were going to just go and run Firestrike in space, but we're actually running like a really sort of well-defined suite of AI machine learning benchmarks, basically just to understand, like, can it be done, right? And then if it can be done, like, how much can you actually do and get out of like the NVIDIA chip just off the shelf. Chris here is actually our lead hardware engineer. I don't know, Chris, if you want to talk about that at all.
I think my mic has been okay. Well, I don't not really. But yeah, I mean, with the Jetson, we it was a while ago. I think back in January or February, it kind of just brought up as an option for like a computer we could use just in general for Bronco Space. And it just happened to come into, like, because it's an ARM processor with a almost desktop class GPU. It'd be interesting to integrate that into accelerating like any processes you would use on a CubeSat, compared to like a BeagleBone, which doesn't have a very powerful GPU, or a Raspberry Pi, which has at least the 4 is like up there with the computing level with its CPU, but it doesn't really have that GPU that can accelerate things like machine learning, which the Jetson platform has been made for with CUDA acceleration. So like some things that we thought it would be good for is like image processing. And for our BroncoSat 1 project, we're measuring its capability with machine learning applications.
Yeah. If you join, I believe tomorrow, Da Cheng is giving his communications workshop tomorrow evening. And if you join that workshop, what you'll probably learn is that one of the big struggles that you get with CubeSats is a really limited ability to actually communicate with it, especially as a student group, when you don't have access to, like, the resources of, say, like NASA or a big commercial company to just hire ground stations around the world. You can interface with, like, services like SatNogs or something like that, which are like open source communities that will just kind of listen for your satellite. But even then, like, you're limited by, like, usually CubeSats run on like UHF some like commercial satellites and higher brow research satellites can go up to S-band or X-band. But the data rates from like UHF, for example, ultra high frequency radio communications, you're talking like 19 kilobits per second if you're lucky. And that's not a lot of kilobits. So if you need to get a lot of data, if you have like a huge amount of data you're collecting, say images, right? Like you can stick a 4K camera probably in a CubeSat, not so hard. But like actually getting those image files to the ground, you can collect a huge amount of data. But the idea with BronchoSat is we're going to deploy like the NVIDIA Jetson and like an AI algorithm to actually be able to pre-sort the data that's collected by the satellite. So we're not going to waste any of our bandwidth on transmitting like bad data. It'll like select images that are sort of in focus and of, objects of interest, and then prioritize those in the data stream. And that's something that's kind of made possible with the GPU acceleration. That's just one example of like the use case. Yeah.
That's really cool. Thanks.
Yeah, no problem. Any other questions?
Actually, I had something. It's more of a comment, really. I remember on Flynn's side, it said F prime was too cool for school for a logo. It actually turns out I just Googled them. They do have a logo.
Oh, okay.
It's very simplistic.
Yeah. Chris's background here is actually the PyCube revision that we made, the infamous polycubed. Actually, Chris, you probably gesture to it and then point out like some of the changes that we've made.
Well, this isn't the full board, just the bottom half because it looks cool. But I move things around just so like it's easier to work with, and I broke out some pins that we would want to use, and it's much more like accessible. So I guess right here are just pins that would be used for like a separate or a secondary radio. But instead, like if you're not using a secondary radio, then those pins would be accessible to you now, rather than soldering like directly to these pads, which is not very secure. I also added, well, just this area in general. This is integrated motor drivers, which we're using for our system of attitude determination and control. They're driving like magnet torquers, and then over here there's just a cutout because the Pi cubed is not it's in the shape of like the PC104 standard, but it doesn't use PC104 interfacing like those connectors. So it's kind of awkward when you're running cables, from one end of the satellite to another, like you're running your batteries or whatever. So we just put in these holes, which are very nice to work with. Those are, I guess, the biggest changes to like what we did for the polycubed. There's also like more on the PyCube by default. There's 2 analog inputs, and I added in some expansions for 8 extra analog inputs. If you're doing like analog sun sensing, if you're not using like a I2C sensor for that, or any other analog sensors for your payloads or whatever.
Yeah. One of the things we didn't discuss during this workshop, but we will discuss during the ADAX workshop on Thursday, is like all the sensing that has to be done by the satellite. There are a lot of things that are probably going to have to be sensed. And when you're choosing your flight computer, it's important to have that sort of in consideration from the beginning. So you select a computer that actually has enough inputs to sense all the things you need to sense. One of the reasons we had to do a revision on the PyCubed is because the original PyCube just didn't have enough ports to plug in sensors to. So that's why we had to, basically duct tape on an extra few.
The kind of unfortunate thing is that BrokerSat 1 was supposed to be a very simple mission, but it kind of exploded into, kind of like things that our advisors and some of our students like thought would be kind of interesting to use. So our solar panels did not have any sun sensors, and we kind of just duct tape them on at the end. And because we're doing that, we kind of need these uh, analog sensors.
Yeah. Yeah, we're not doing like a workshop on like CubeSat project management, but if there was one, right, the title would just be scope creep, right? For anyone who's not familiar, scope creep is the concept of like, so the scope of a project is like how much you're trying to accomplish, right? Ideally, every good project should begin with like a scope of work where you say, okay, this is exactly what we want to get done, right? And in a perfect world, you would get exactly that much done and nothing else. But unfortunately, in the real world, especially with the university space mission, there will be scope creep because the people who are giving you money and resources will want more out of you than you originally wanted to tackle. And that's something you just got to kind of deal with. For us, like we had to scope creep in like magnet torquers and sun sensors and things like that. But yeah, I think it's pretty rare to find like a university space mission that at some point does not go through like a major revision, right? Whether that be like changing the mission objectives or like adding new features. It's just sort of like a result of the learning process. Because something that definitely happened with us, right, is like the first design that we made, like there were a lot of things like we didn't know were going to be issues until we actually produced it and then started testing it, and then we're like, oh no, right, like you can't read and write to the SD card at the same time. Well, we gotta tack on a fix for this, and stuff like that you're just gonna discover, and that's just a part of like what you have to deal with as a university CubeSat group. Yeah. Any go ahead, Crocus.
No, just behind me is what
are you going to talk
Sat
about
One
originally
looked like. Actually, this does come into something that was mentioned earlier in the meeting, is solar cells. If you're developing very cheap CubeSats and you want to have cheap solar cells, in the past, some teams have used these triangular scrap cells that are space grade. They're just the scraps that came off of cells that they sell.
Yeah, like when solar cells are made, at least silicon solar cells, they come out in these like circular wafers. But unfortunately, if you've ever just like we're familiar with shapes, circles don't really like pack together that well. Ideally you want squares, right? Because squares pack together really well. Or hexagons. Hexagons are pretty good too.
Okay. Well, whatever. What I was trying to get at as companies like Azure Space, well, I think maybe not Azure Space, but Spectra Labs here in the States, they don't sell these triangles anymore, which is kind of unfortunate. So that's why we had to change from this design to those standard square ones that are in the diagram behind Michael.
Yeah, and you'll see, of course, there are two satellites, because when we first started, we thought it was going to be so easy that or so simple that we were going to make two, and then actually we were going to say we were going to make five, but we were going to have two that we're going to fly. That kind of comes down to another sort of point though, which is if you decide to not go the commercial route, right? Like you're not going to buy like the $8,000 ISIS computer, and you go for something like a BeagleBone Black, it only costs like maybe $200, right? Something like that. Definitely have multiples. Like for BroncoSat right now, we only have 2 copies of like the hardware in the satellite. But like we have like I think probably 5 or 6 Jetsons floating around, right? Because and I think we literally have like 9 pi cubes, right? Or 5 pi cubes and 4 poly cubes like floating around. Because when you go for the more low cost option, you're able to have a lot of copies, and then copies aren't just good for like if something breaks you can replace it, but it's also good to just be able to do a lot of testing in parallel, right? So you don't have to like wait on one test to finish to go to the next test. Like time spent testing is a really important thing. Like a really high number of CubeSats, it turns out. Like I think the number is like 80% of missions that fail in the first month. And if you can kind of get past like that first month, that like infant death, then you're probably gonna be fine. And so like, yeah, we are kind of blowing through. We've blown past the time slot. Are there any more questions? Like,
I just had one more.
Yeah, go for it.
Flynn mentioned earlier about test frameworks and testing, automated testing. What systems were they using at NASA the most? Was it Jenkins or was it something else? Or
I have no idea. Unfortunately, Flynn had to run, which is why I'm just kind of running this right now. But I mean, you can definitely just add him on the Discord, and I'm sure he can just answer.
Okay.
Any last questions from anyone? Okay, if there aren't any questions, then I think we're probably gonna wrap it up. We just had the one workshop today, but tomorrow I think we actually have 3. Do we have 3? Yeah. So tomorrow we actually have 3 workshops. One which wasn't originally announced when we started the hackathon because we just got it not too long ago. The folks from MathWorks, the people who make MATLAB, are actually going to come down and do a demonstration of how you can use the simulation libraries inside MATLAB to simulate a CubeSat design and a CubeSat mission. That's pretty cool. Then we are also going to have Da Cheng delivering a workshop on communication systems and, you know, how do satellites how do you talk to your satellite like from the ground to space? And finally, Arshia is going to be giving a workshop on the space environment, right? Like what kind of struggles, right, are you going to deal with, like thermal complications, the vacuum environment, things like that. And yeah, that's about it for now. And the space environment one is at 6 p.m. These are all on the website, but they're also in the Discord, right? If you just go to the channel for each workshop, you can find the time there too. And if you all have any questions, you know, of course, feel free to reach out to us. Yeah, I'd like to thank everyone for taking time out of their, you know, early 2021 to join us, and I look forward to seeing everyone again in the next couple of days. Have a good evening, y'all.
Thank you.